All right, we're going to continue and look at part B of the question we started looking at in the area and volume video 1. So this is now finding volume by cross sections. In this case, the cross section is an isosceles right triangle, so the two legs are the same size, with a leg in region R. That means that the slice that we draw through region R, that length, is going to represent one of the legs of the right triangle. And since it's a right triangle, right, the length of that slice, upper y value minus lower y value, since it's a right triangle, the base and the height are both the legs. So since that leg is the 4 minus f of x, the area is 1/2 base times height. But as I just said, base and height are both the legs. So I have an area formula. I just have to write the definite integral, 1/2 base times height. The 1/2 comes out of the integral, and we go from 0 to 2.3 of 4 minus f of x squared dx. Again, those limits of integration are the same intersection points we used in part A. Go to the calculator, work this out, and we get the 3.574. On to part C. Part C is fairly easy. You've got a vertical line that divides region R into two regions with equal areas. So vertical line at x equals k. And the area on the left side of that line is equal to the area on the right side, wherever that line happens to be. All right, so you need to set up an equation. Remember, equations have equal signs. If you don't have that, you're not going to get credit for it. And you just have to set it up but not evaluate it. You don't have to solve it. So on the left side, you're going to go from 0 to k. You already know what the height of your rectangle is from part A. And you're just going to set that equal to the integral from k to the other intersection point, 2.3, same height. It doesn't matter whether or not you know how to solve this, right? If you had to solve something like this, you'd have to anti-differentiate and substitute k in and then solve for k. If you had to, that's the process you would do, but you don't need to do that here. You just need to write this and you're done with the problem. Fairly straightforward. All right, so we're going to look now at question number 2, which is really specifically a BC area and volume question because it involves, in figure 2, an unbounded region. That region W goes on to infinity, and that is specifically a BC calculus topic because it involves an improper integral potentially. All right, so you have your two functions here. Region R is bounded, region W is not. Your starting and ending points for region R on the x-axis are 1 and 5. Region W starts at 3. All right, so find the area of region R, part A. That's fairly straightforward. We're going to, again, draw a little slice to get the height of our approximating rectangle. That's the upper y value from y equals 1 over x minus the lower y value of 0. And then we just write our integral with that. Here we already have our limits of integration, 1 and 5. And even though you're not allowed to use a calculator here, this is fairly straightforward. The antiderivative of 1 over x is natural log of x. And you're going to evaluate that from 1 to 5. So you wind up with natural log of 5 minus natural log of 1. But natural log of 1 is just equal to 0. So write it out as natural log of 5. That's one you definitely should know for the exam. Right? Log of 1, whether it's natural log of some other log, is equal to 0, and you can eliminate it from contention when you're doing something like this. All right, on to part B. Now region R, same region, it's the base of a solid, and each cross-section perpendicular to the x-axis is now a rectangle, but they give you the area. You don't need to find a formula to represent the area. They're giving it to you, which is nice, but the thing that they're giving you is going to require something that's perhaps a little more tricky than an AB level question. So here's the setup again, right? And there's your integral, right? Volume by cross sections is the definite integral from A to B of the area of one cross section times the thickness of the slice, and that's dx in this case. All right, well, you've got an x times e. that is a classic setup for integration by parts here. So we're going to let u equal x, du is of course dx, and then dv would be the other e to the 1/5 x factor, and when you anti-differentiate that, you wind up with 5e to the 1/5 x. Now, when I write my formula out for integration by parts, and I do my substitutions, uv becomes that first term, and vd, the integral of vdu becomes the second integral there, which is a manageable integral. Here's the thing you have to remember when you do integration by parts with a definite integral. That uv part that's no longer in an integral, you still have to evaluate that using the fundamental theorem of calculus. So you have to do the antiderivative for the integral ones, but that uv term you have to evaluate at the upper limit of integration minus that uv term evaluated at the lower limit of integration. I know that's strange, but you just have to remember, since it started out as part of an integral, you have to follow all the integration rules for that. Now this, you can finish this one up on your own. That would be your antiderivative for the integral part. And when you substitute 5 and 1 in for each of those expressions, you get a little cancellation that happens here. The 25e's cancel out, and you wind up with a 20e to the 1/5 power overall. That is part B of this question. And let's move on to the next. All right, part C, find the volume of the solid generated when the unbounded region W is revolved about the x-axis. So again, you're doing volume. The x-axis is a boundary here, so it is the disk method that you're going to be looking at. Let me make this a little easier to work with here with the space. So because of that integral goes to infinity, this is an improper integral. So you're going to have to just follow the rules for an improper integral and see if we get an answer here. Because x-axis is our boundary of our region, it's also the line of revolution. We use the disk method. Our radius is 1 over x squared. Just like any other disk method, the only difference here, at least at the start, is that the upper limit of integration is going to be infinity because it's an unbounded integral. So we wind up with this by the disk method. And of course, the way improper integrals work, you have to rewrite it as a limit. That pi in front of the integral can go right in front of the limit. Right? You just pick an arbitrary letter. We've been using b in class. So the limit as b approaches infinity, and then you write your integral from 3 to b. And that allows you to actually work with the upper limit of integration, since we're assuming it's a real number and not infinity, just something that's approaching infinity. All right, so now you anti-differentiate. 1 over x to the 4th is x to the negative 4th. Antiderivative would give you that. You evaluate this, the limit, of this at b and at 3. The term that has b in the denominator, as b approaches infinity, that's going to go to 0. So you wind up with 1 over 3 to the 4th power times the pi in front of the whole thing. So you get pi to the pi over 81. And that is the rest of question 2 there. So in the next video, we'll look at questions 3 and on from there.